Good morning, students. Welcome to Design Laboratory. So, in the last video, we have seen how to conduct the experiment, simple pendulum. So, from that experiment, we need to note down these values, that is the diameter of the small ball, big ball, and the weight of the small ball and big ball. So, in the observation table, here we have measured the length of the thread, and the length of the pendulum will be L plus R, and the number of oscillation we have taken it as 10. So for 10 oscillation the time period was 13.29. Likewise, for a different length of the threads, you need to note down the time period for the 10 number of oscillation. Then from that we will get the time period. The same procedure you have to follow for the big ball. Only thing is you need to change the ball here, and for the different lengths again, and for 10 number of oscillations you need to note down the time period. So the calculation part is, so first for the small ball, the time period T is given by T by N, where this T is time required for 10 number of oscillations. So N is number of oscillations. So if you consider the first reading, so there the time was 13.92 seconds. So divided by 10, so the time period is 1.329 seconds. Similarly, for the second and third readings, you get the time period as 1.11 and 1.584 seconds. Then you need to calculate experimental frequency, that is omega experimental is given by 2 pi divided by T, where this T is a time period. So the first time period is 1.1329. Substituting that value in this equation, you will get omega experiment as 4.72 radian per second. Similarly, you substitute the remaining time period, the same equation, you will get omega experiment for the different time periods as 5.63 and 3.966 radian per second. Then you need to calculate the theoretical frequency, that is omega theoretical is given by root of G by L. So here G is 9.81 divided by L is from this table, the length of the pendulum, first reading. This calculation is for the first reading. So 0.4025. To substituting, you will get the value as 4.936. Similarly, for the second and third lengths, you need to calculate the theoretical frequency. Then you need to calculate the percentage of error with respect to experimental natural frequency is given by omega experimental minus omega theoretical divided by omega experimental. So here you substitute the first values, that is for the first time period value. To substitute, you will get the percentage of error as 4.576. Likewise, you are having 3 sets of readings here. You substitute those values, you will get these values. Then the fifth one is percentage of error with respect to theoretical natural frequency is given by omega theoretical minus omega experimental divided by omega theoretical into 100. So again here also you substitute the 3 sets of readings, you will get 3 set of percentage of errors as 4.9 percentage, 0.7 percentage and 6.3 percentage. And this is the result sheet. So for the small ball, these are the experimental natural frequencies, and these are the theoretical natural frequencies, and these are the percentage error with respect to experimental natural frequency and with respect to theoretical natural frequency. So here I have shown the calculation only for one set of reading. The same procedure we need to carry out for the remaining these values, that is for the second and third, and the same procedure we have to repeat for the big ball. The thing is, we need to take the corresponding values while substituting the terms in the equations. And if you have any doubt, you can leave the comment in comment box. Thank you.